Okay, thank you very much for being here. My name is Michael Halverson, Chief Engineer for the Alabama CubeSat. We have a spacecraft seminar series on cybersecurity for space missions, a primer into this topic delivered by Duncan Greaves, who was a cybersecurity expert that we met at a conference a few years ago now. We are incredibly happy and thankful to have Duncan here. Duncan, would you please take it away?
Thank you very much, Michael, and thank you for the invite. Cybersecurity for space missions, a primer. Um, I'll tell you a little bit about myself. We'll go through the agenda. But essentially, what I want to cover in this seminar is about step-by-step decomposition of how cyber risk management works, how the process works, and how we can incorporate the findings and patches into our systems models and missions. And it's also a very practical based guide because it's based on my experience working with the European Space Agency. And we've included a little bit of the standards, a little bit of theory where it's necessary. It's also quite a bit of supporting material, which I've referred to at the end of the lecture. So without further ado, the agenda of today will be first off a little bit about myself and my pathway into space engineering, with an introduction, setting the context for cybersecurity, looking at risk management because we'll be following a risk management-based process. We look at how we model threats, cyber threats to missions, and what our possible responses are, and how we can work those into the mission engineering. And then we move on, if you like, to certifying and accrediting and assuring those changes, and a little bit of conclusion and further research directions, as is normal for this kind of thing. So, thank you. So presenting today, I'm presenting from the University of York. The University of York is one of the Russell Group of research intensive universities in the UK. And it is famous, if you like. The computer science department is famous for its work on systems and safety engineering. There is an Institute of Safe Autonomy that's looking into AI and robotics and safety in safety critical systems. So that's about the university. About myself. I'm the program leader for the University of York online MSc offering in computer science and cybersecurity. But I've not always worked in computer science. I started work, I graduated in engineering geology and worked for Halliburton Energy Services in the North Sea, which is hence the map behind me, which is the map of the North Sea oil fields. But I retrained because oil platforms were becoming full of computers. So I retrained as a software developer and then worked for the next 20 years or so, working as a software developer and architect in the UK, but also in Australia, working for large companies. Finally, or maybe finally, I retrained again and did my PhD in cybersecurity management. And it's a model of trust in socio-economic environments. So you may find this thread of trust running through a lot of the things I talk about today. It is important, and I hope to show how we foster trust, how we elicit trust in our systems through the processes that we follow. So my space project engineering, I worked as a research fellow for the University of Warwick in the UK and worked with the ESA-sponsored SSE for space. This is Secure Systems Engineering for Space. They were looking at a methodology which could support cyber risk management and contribute to the technical standards that they maintain. Technical standards for ESA are maintained by an organization called the ACSI, a little bit like the CCSDS over there in the USA. I've also done some work on the UK Space Agency projects on resilience, the Resi Space project, and presented the findings, if you like, on this methodology to participants from the Philippine Space Agency in Manila, who run a series of weather and geographical tracking satellites. The qualifications, which I think have been really helpful for me, making this transition through to space engineering from oil engineering. Obviously being curious, but I'm qualified in TOGAF, which is the Open Group Architecture Framework. It helps me to set problems in context very well. I'm also a CISSP, which is Certified Information Security Practitioner, which is run by ISC2. It's kind of an exam-based membership organization, but also project management. Project management seems to underpin everything that we do in this sphere, so it's important to have an in-depth knowledge of that. So on to the introduction to space cybersecurity. I'm going to introduce the subject, talk a little bit around the general subject of cybersecurity, just to help you frame in, help you to get into the subject a little. So, cybersecurity affects all machine systems, but it's influenced by particular contextual factors. So some of these factors that apply to space missions are that they're high value, they're very visible, they potentially last a long time. So if, for instance, we're implementing an encryption algorithm, it may well be that what appears to be a strong algorithm today will be a weak algorithm in a few years' time. There's a limited bandwidth and data frame size because of the necessity to communicate with the ground-based stations. And also the dynamic systems behaviors are exceedingly difficult to model. I'm sure you understand that when machines are in flight, when they are geographically dispersed, they sometimes display behaviors that we haven't already modeled. And so it's difficult to model some of these things in advance, especially when it comes to protection measures, things that might happen, not probably happen, but just might happen. So looking forward into what is now known as new space. So the number of space missions, number of satellites in orbit has rocketed, as you might say, from being largely government sponsored, large big box efforts to the more recent developments where, let's say, high net worth individuals or corporations and commercial interests are becoming involved in the commercialization of space. This increases the number of launches, the number of satellites, but also the variety of technology that's in operation is much wider than it used to be, and presents therefore a greater attack surface to any potential cybersecurity hacker. There's lots of different threats, lots of different areas in which we can be compromised. These are just a couple that I've picked up from recent kind of news posts. The first is the HackerSat. It is sponsored by the European Space Agency, where teams try to hack a satellite and they can win points and prizes. It's very popular culture is hacking, and this seems to tap into that. The other is, if you like, a data breach that affected a supply chain company. And you always got to be aware when you're working on space missions, possibly you'll have a principal contractor and many, many subcontractors, that there is a potential risk from a data breach or cybersecurity attack on any of those system participants. So where can it go wrong? The first thing really is to understand your mission and which segments will be involved. This is taken from the CCSDS, I believe, but each segment needs protections of its own, and the links between the segments also represent areas which need to be thought about in a cybersecurity context. Obviously, the more complex the mission, the more complex that application of any process to do with security is going to be. But it needs to encompass all different assets that are going to be used in the mission. The other assumption I'm making, of course, is that cybersecurity is a human problem. It's not generally a problem that hits us from outer space. It's other humans that are trying to enter our systems that present the problem here. So how would we define security? It's a very difficult to define variable because it depends on many different things. But essentially, the trustworthiness that is given by an information system, by a computerized information system, will afford the confidentiality, integrity, and availability. This is, if you like, 101 of cybersecurity. Confidentiality meaning it's not spread far and wide, integrity meaning changes aren't made in an unauthorized fashion, and availability, as its name suggests, is available all the time and is not prevented from doing its job by anything else. Sometimes people are doing things like authentication, non-repudiation, unauthorization. Arguably, these are facets, if you like, of confidentiality, etc. But they all need to be thought about during the design and build process. And I say the security, if you like, emerges from building these trustworthy properties into our systems. Also, I'm just going to touch on whether cybersecurity is a subject at all in itself, or whether it is cross-cutting. There's arguments on both sides of this particular fence. So cybersecurity can have a body of knowledge, the cybersecurity body of knowledge you may have heard of. It's if you like, a catalogue of the different tools we have in our tool set. So this may include things like encryption, authorization and authentication schemes, but it's kind of depends whether it cross-cuts into other fields. So yes, here are the tools, but we apply them to say safety engineering, systems engineering, dependability, reliability, etc., in order to secure the system as a whole. The security comes out of everything being secure and working in a correct fashion. As I mentioned previously, the standardization for ESA, the European Space Agency, maintained by an organization called ACSI, European Cooperation in Space Standardization, and they have lots of downloadable materials, documents, that cover the major areas that I've listed here. There are lots of documents, not all are available freely, but if you register with their portal, you will be able to download the specifications and standards that apply in European space systems. Okay, so why are we actually bothering? Why are we doing this protective work? Because it doesn't, generally speaking, add much to a mission. It just makes us more secure. It may improve the chances of success, which is always a good thing. But what it is doing is it's protecting the services and the facilities that have become part of our national infrastructure. So things like communications, remote sensing, geo monitoring, new technology experiences like autonomous vehicles, tracking, shipping, rail signaling. It helps to extend our knowledge about the world we live in or the universe we live in with the deep space missions. And increasingly, it's been used not only in existing commercial airlines, but also the business, if you like, of launching, tracking, and maintaining the space infrastructure that's already there. And this, again, is without any of the, if you like, dual use facilities of satellites, which can be used in military or other scenarios as well. So we need to protect these to protect what we have already, if you like. It's not always it doesn't always make it onto the critical infrastructure list, but I think it's an oversight and certainly an area which needs focus. So how do we actually measure security? I've kind of touched on this a little bit. Security doesn't come in little packets like securitons or anything. You can't see the security. It's actually an emergent property of the system we have created. So it's the components, the functions, the interfaces, the way that these work together seamlessly and without compromise that makes us feel secure and assured that we've done all we can to protect our safe space missions. Also, it fits in with, because a space mission is a system of systems, even the smallest satellites have several systems collaborating and working together. It's necessary to build these from components upwards. Those components go into other components, which form systems. Those systems form other systems. So it's a nested dependency that makes us secure. And part of the process that I'm going to describe today is about how can we independently verify that these security measures have been taken. It's easy to say, we've done this to add security. How do we actually check that that's there? How can we test that that's there? Okay, so first thing to do, or first thing I'm going to do is talk a little bit about mission context. Every mission is different. Even similar missions are different. So we need to look first off at the start point, the inception of a mission. It usually has business drivers and business impacts. So a mission is set to, let's say, go to the moon, and it's going to go and it's going to carry out various inspections or record various things, and that is the purpose, if you like, the business purpose. What are we going to get out of it? The decisions about spacecraft are always made in mind with risk appetites and risk tolerances. These are particular to any particular organization. And they're also like social constructs. So it's how much risk is an organization, a space agency, or a company willing to undertake in order to complete this mission. When I talk about these things like risk, appetites, and tolerances, I always think of like speed limits on a road. So the risk appetite is what I'm comfortable with doing. So it might be a 30-mile-an-hour road. So 30 miles an hour is my risk appetite, if you like. The risk tolerance, if you like, is where alarm bells start ringing. It might be where the police start to stop me because I'm driving too fast. Maybe that's in the UK, that's around 35 miles an hour. That's the risk tolerance. So we can put up with a certain amount of risk above what we are comfortable with, but once it reaches a certain level, we have to take measures. And our risk capacity, if you like, is the uppermost limit. If people are driving on that 30-mile-an-hour road regularly at 50 miles an hour, if there are accidents on that road, then further controls, further safety measures need to be taken. in order to limit that risk and ultimately the failure of the mission. So how much risk can we stomach before we start to take controls, make more controls? So we need to bear in mind the business and security objectives. We need to bear in mind the requirements of what we need for a mission. And we also need to think about treatments and controls, which will ensure the security of those operations and functions so that those requirements are met. And then finally, having built our systems, how are we going to measure them? How are we going to know, or should I say, how do we know that a system is secure? What are the certification, accreditation, and assurance requirements? And how do we go about doing that? So this slide, if you like, is taken from the SABSA Blue Book. Those of you who are not familiar with SABSA, it's a business attributes framework, security framework, which maps between the business drivers and the security attributes. And it does this using business attributes. It's a large book. It's got lots of different attributes in there for the systems that you're developing. So this example I've given is that we want to create a reliable satellite navigation service. Therefore, the business drivers are stated. It's got to be lawful, it's got to be accurate, it's got to be resilient. But in order to achieve that, the systems that we employ need to have the following business attributes. So they need to be compliant with the law, they need to have integrity, they need to be continuously available. And these, in turn, map to the security attributes that are required. The confidentiality, the integrity, the availability that I talked of earlier. So there's quite a lot of, if you like, thinking involved in translating what your business drivers are to what your security attributes or what your security drivers are. But you have to think about the implementation before the implementation takes place in a lot of cases. So again, I'm trying not to overload you too much with jargon, but I'm hoping here in this slide to show that the mission and its levels of protection that are required are met through security controls. And we do this by passing it through various stages. So you start off with a mission, low, medium, high security. This is generally stated in the mission mandate. You will know what level of protection your mission requires. Based on that, you will come up with some security objectives. Security objectives, if you like, are statements of what the system needs to do security-wise. These are generally not technically based. It might be just something like the communications should be protected with 128-bit encryption. That's the statement. It doesn't say how it's done, or it's reasons from the mission that needs to be done. So in order to meet that requirement, that security objective, we need to implement lots of different controls, several different controls. So in the example, where we're talking about encryption of communications, it might involve software modules or hardware devices being applied to the satellite in order to scramble and unscramble the messages which it receives. And these are all contained, if you like, in the requirements profiles, the security profiles. So we gather together, if you like, all of these security measures and then apply that security profile to our system. In a lot of ways, I always think that the security controls and the security profiles are the only real parts of this system. These are the things that we're implementing in order to make the system secure. and in turn meet all these security objectives and these protection objectives in order to meet the ultimate aim, which are the business objectives of the mission. So we'll talk a little bit about protection profiles. So a protection profile is implementation independent set of requirements for a target of evaluation. Now, a target of evaluation can be the whole system, or it could just be, let's say, the navigation system or the photography system. Each of these can be considered. And it's common in many other areas, let's say like power generation, in order to, the certain components are tested independently in order to give an assurance that they work and will work in their operating conditions wherever you put them. For instance, if I have a circuit breaker for a power station, it will undergo a lot of certification and testing before it's allowed first in one power station, but after that as a product within other power stations. But it's the functionality of that circuit breaker that is the important thing, not how it works. It just needs to do to break the circuit. It's the same with the protection profiles for security. We're not really concerned how they implement encryption for a protection profile, just that they do. It's a set of high-level requirements. Often, people in the USA will refer to the common criteria, which has 9 assurance levels, and you select an assurance level at which you feel comfortable, and then you work your product toward that level. In Europe, with the ESA, and ENISA, which is the European Cybersecurity Agency, they have 3 levels, only 3 levels of assurance that they work to, but the concepts underlying that is similar. So what we end up with at the end of our security analysis and security assessment is a collection of security controls tied together to meet those requirements in a security profile. And then that security profile is applied to the engineering, to the systems, and at that point, you can test against your assurance requirements. Does it actually meet the requirement that I've stated? So it's again, hopefully clarified in this next slide. So a protection profile, if you like, is independent from a security profile. A protection profile is theoretical. I want to impose 128-bit encryption on my system, but the security profile, if you like, is physical, for want of a better word. It involves the functions of the software, the functions of the hardware, and everything you need to do in order to meet those requirements. The requirements, if you like, the objectives are given in the center of this picture. And you can see how this is going to build. So there's the, on one hand, the theoretical, so to speak, security protection profile. And on the other side, there is the implementation, the security profile. So we can compare how one against the other. So we can see how the security profile meets the protection profile, how it meets those objectives. And likewise, our protection profile will compare what has been implemented to see that it meets the required assurance level. Okay, just take a breath there. Okay, and also this, just to complicate things a little bit more, systems are start from designs. They start from components, generally speaking. You get the components of the system, you pull those together into subsystems. Those subsystems are developed into the final system. And that is then deployed, and finally it's operated. Once a satellite has been launched, it may be in orbit for several years, and therefore this kind of cycle needs to incorporate all of those changes. So it's a lot of changes happen between inception and production of a space system. And we need to keep track of all of those to ensure that they're carried forward and tested at each stage. So I talked earlier about things like risk tolerance, risk appetite, all part of risk management. Are the risks that we're undertaking necessary? Are they acceptable? Or do they exceed our risk appetite and need further controls to be added? So the risk management part, again, is not something that's exclusive to space missions. Risk management is part of things like banking, railway management, all kinds of industries use risk management, and they use that as because the language of risk management cuts across business and IT. It cuts across business and IT and engineering. If we can use this common language of risk to talk about what we need to do in a project, then it aids decision making and analysis and modeling. Okay, so kind of the purpose of risk management, it ensures compliance. A lot of industries require you to show that you are compliant with various regulations, and it builds in what's commonly known as security by design. So we're not adding on security afterwards. Ideally, we're building it in as we go along. That's not the start. So this means that the risk tolerance is always maintained within our risk appetite, and it kind of risks can arise at various levels in a system, all the way from the smallest component like diode failure or software function failure, all the way up to major malfunctions in larger components. So we need to carry up, if you like, all of our lower level risk assessments to the higher level in order to maintain and assure the security we've got. There's kind of, it gives, if you like, a work in motion. It's a work in progress. The risk documentation should always be updated every time that the system changes. And it must be easily understandable by all partners that need to understand it. Again, this is a big major plus in, let's say, a large space mission where there's lots of primary and secondary contractors that are involved. Okay, so when we look at risk assessment, we need to look at where we're most at risk. Where are the vulnerabilities and weaknesses in a system? And we need to conduct an assessment that enumerates and evaluates the vulnerabilities and weaknesses. Now, I've not actually seen any definitions about what's a vulnerability and what's a weakness, but I tend to think of vulnerabilities affecting smaller components or components. It may be a bug in a software function that could be patched, for instance. But a weakness is more of a systemic problem with a system. The example I always give is that a SQL injection attack is a systemic weakness. It's a weakness because every system that uses SQL as its query language is potentially vulnerable to an SQL injection attack. Unless, of course, you take controls, you add controls into your system. So what we need to do is we need to evaluate the vulnerabilities and weaknesses and take action in order to manage that risk, reduce or mitigate or completely eliminate those risks from our thinking. In the European Space Agency, they often use the ACSI risk management toolbox framework, which I believe is publicly available. But on the right-hand side of this slide, I've actually borrowed a diagram from the NIST. I think it's NIST 40 about risk assessments, NIST SP 800-40. These kind of standards already exist. It's just how they're employed in the methodology. So let's map our security interests, if you like, to a fictional mission, which goes from the initial analysis and feasibility through to the definition phases, through qualification, production, through to operation, and finally, the retirement of the system. There's certain areas here marked in red where the security team is definitely involved. It's true to say that security should be considered from the outset, but often when the business drivers and the business needs for a mission are being assessed, the security needs aren't the primary aim. It's only when you know what you're working with that you can actually start to fill in the security requirements that you need. And then through the creation of these protection profiles, you can start to develop the certification and accreditation requirements that you need. So alongside us building our security profiles, we're also building our protection profiles so we can measure how well we have combated a certain risk. And then finally, at the very end, we have here what's called security assurance. I'll touch on this a little bit later, but this is the ongoing security procedures, processes that you need to undertake in an operational capacity. Once a spaceship is up and running, there will be a security operations team that deal with day-to-day security alerts and other items that may occur. It also assurance is this idea that we've gained and reached a certain level of trust, and that trust is maintained by a maintenance facility. So how might we even start doing this? So like I say, systems are made of subsystems. Subsystems are made of further subsystems. Those are made of components and elements. So you're managing here a system of systems, and that is the approach we're taking. When we're developing software, for instance, secure development lifecycle is used. So there are certain techniques that are used in software development to avoid and mitigate cyber problems. I was recently watching on YouTube about there was a failed launch of the Ariane 5 rocket back in 1996, I think it was, where a buffer overflowed. The new rocket went faster than the old rocket, but they didn't upgrade the software to extend the size of the buffer. And this buffer was maintaining the airspeed, but once it reached a certain point, it was going too fast. It overflowed that buffer, which reset it to zero. The system, thinking that it had been a major malfunction because the airspeed went to zero, then self-destructed. So it was a built-in security safety mechanism that, if you like, finished the mission off. But the problem came from a software function that was buried deep inside the code of the mission computer, or the spacecraft computer. Everything worked to plan, but this gives an example of the kind of things that a cyber hacker might be looking to do. They might be looking to do a buffer overflow attack, and then that would kick in the safety systems. Okay, so we need to understand what the implications are of the subsystems when we're designing systems, and then consolidate it all in order to achieve a top level overview, a whole system, a holistic security view. Now, in the European Space Agency, they generally, contractors use Agile and Scrum systems methodology because it's quite quick and iterative, not only for building the systems, but also for building the security controls too. And there is an interesting software requirements standard available. Okay, so revisiting our earlier slide about the mission life cycle across the top from initial analysis to retirement. How do these feed into each other? So it's kind of what I'm looking at here is we identify the risks and categorize them. Then we see if that falls short of or presents a threat to the assurance levels that we require. And if that's the case, then we'll put in controls. What I put as security risk treatments. So treatments are controls. Those might be technical controls like patching software, but they might also be human-based controls like taking backups or strengthening authentication techniques. And we carry on, if you like, with this cycle. We keep building our security profile of controls, and then we can measure them against the required assurance level. If they're still short, we need to put more controls in and then reassess and retry. But these all build up into a richer picture as we go from start to finish of a mission. It starts to build a richer picture of the context and the capabilities of what we're building, what we're achieving. Okay, so one of the techniques that's most commonly used in association with risk management is cyber threat modeling. So this is looking at building a model in order to guard against the action of a bad actor against our assets. So we identify the major assets, the primary and secondary assets. The primary assets might be things like information, as well as physical assets like rockets or hardware. And then we run a threat and a vulnerability risk analysis assessment. So we assess how well they meet these criteria of CIA, of confidentiality, integrity, and availability. This way we can evaluate in a targeted way the threats which could potentially stop us reaching our business objectives. These can be done at system and component level to model the risk at every level. And it can become a very significant undertaking. Anybody that's looked at how many security vulnerabilities there are out there would understand that you need to be able to filter those down according to which system you're looking at. But there are guidelines. There's lots of different guidelines and lots of different frameworks. I'm thinking of the MITRE ATT&CK framework, MITRE defense frameworks, but other frameworks are available, ISO controls, NIST controls, etc. So when we're modeling a threat here, and this picture here has been sourced from the CCSDS, the threat source agent, it's like I say, it's people that's the problem here, not the engineering. It's not generally the aliens that are the problem. It's other humans that wish us ill or want to damage our assets. These can be the people that are doing this can be grouped broadly into the kind of behaviors they have. So you might have what's known as a script kiddie, which might be somebody that just downloads scripts from the internet and tries it against various vulnerabilities in systems, right the way up to foreign governments that might organize to have missions fail or not complete correctly in order to fulfill their political objectives, and various other things in between. So again, the threat agent will target vulnerabilities in the components, weaknesses in the systems that make up our mission in order to cause an event, to cause something to happen, which is not desired and not within our mission parameters. So at least modeling is one way in which we can think about who might be. Oh, oh, I'm just seeing what's happened there. I think that's PowerPoint 365 problem. I'll just
Great
start
job,
that
Microsoft.
again.
No changes.
I'll just get that started and then I'll try to share it again. Okay, on the screen. Uh, am I sharing again? I think I am.
That you are.
Brilliant. Okay, so I will very, very quickly do all of this stuff. Okay, so yeah, threat agents target vulnerabilities or weaknesses. If they're successful, then that has an impact on the mission. Okay, so threat modeling actually is a way that we determine what we will require. What are the controls and treatments that are required in order to ensure, I should say, the confidentiality, integrity, and availability. And they fit into various categories. Again, I'm borrowing from the CCSDS. Their threats to space missions is a good read. I would recommend that. It's the Green Book, 350.1 or 2, I can't remember. But you know, things like jamming and interception are particular to space missions, ground facility attacks, and incursions, shall we say, intrusions, data corruption. These are more common in across different systems. They're not limited to space systems. But we can think of various mechanisms that can reduce the threats using check values, data integrity values, and we can make a reasoned assumption about how likely that is likely to be. What is the probability of that happening? Now, this is quite subjective, so I would recommend discussing that with as part of a panel or a board or with experts to see which are the most imminent or strongest threats to your mission. You've got to, again, while you're taking risk-based approach, you've got to approach the highest risks first to reduce those, and then work your way down the list, if you like, until you're comfortable that the risk you are running is back within your tolerances, back within your appetite. So we get this list of requirements. We need to, for instance, have an integrity control on our data. So we then select a security control that can meet that in the terms of data integrity. It might be a patching algorithm like SHA 256, for instance, and that will meet the requirements of the protection profile that we're doing. Also, every threat affects confidentiality, integrity, and availability differently. So we've heard of denial of service. That reduces the availability of a system. It might not impact the integrity and confidentiality, but it reduces the availability. So you can grade, if you like, each of these variables in order to evaluate what is the impact and the probability. Where is the risk? How can we evaluate the risk? Also, you can derive from these potential threats further assurance requirements that would go in our protection profile. The system needs to defend against this type of attack or this other type of attack. There's a lot of information on this. Again, the CVSS database that I've given a link to here actually quantifies the confidentiality, integrity, and availability problems that each of these vulnerabilities might bring, and that will get you towards finding a solution. Okay, so having decided what we need to implement in terms of requirements, and then added our security controls in. What kind of responses can we have? So what kind of responses do we have? So what we need to do, like any other system change, is we need to identify what the risk level is before we start. Then we need to identify which of the options is best for us in combating that risk, which of the controls are the most useful, and then applying those risk controls and seeing whether that actually reduces our level of residual risk. Risk very rarely goes to zero, but it certainly comes back within our appetite. And if those controls that we selected aren't strong enough, they're not doing the job that we need them to do, we look at other controls, stronger controls, in order to meet those requirements. Different types of treatment options include modification, retention, avoidance, and sharing. These are elaborated in further detail in the ISO 31000. But you can retain a certain part of that risk if you need to. You can avoid the risk by doing something differently. You can share the risk, maybe by insuring it or passing functionality between two modules, so that if one's compromised, the other isn't. Or you can modify that risk in some other way. Then, of course, having chosen and applied your controls, you need to update your security profiles. So all of your requirement deliverables, everything you're going to deliver in order to deliver security needs to be updated. In ESA, in the European Space Agency, there is a great deal of committees and boards that approve and assign security profiles to components. It's a necessary part of ensuring that security is strong, and if you like, a consensus occasionally needs to be reached as to what level of security needs to be in, what security controls need to be going in. Once you've made changes, like if you made changes to any system, if I was to add an extra cylinder to my engine, I'd need to go and re-verify that would be has not affected the operation of that piece of equipment. So re-verification, retesting, and there's lots of different places where you can close out those problems and record the evidence that you have actually tested and re-verified. Then you need to look at things like configuration management, because it may be that in changing one part, you may need to have to change an associated part. You need to make sure that those two changes go in together. And then you record in your risk register that you have reassessed that risk. So an assessment, add a control, re-verify, reassess. It's this kind of cycle of check, do, what do they call it? Plan, do, check, act, where you're constantly improving, if you like, so that you can meet the requirements that's needed. So then we get on to, if you like, the idea of certification, accreditation, and assurance. These slides are a little bit more text heavy, but I'll try to convey what we're doing when we're certifying, accrediting, and assuring, and why that is important, especially for trust. So we talk about establishing trust, so we produce trustworthy systems so that we can trust them. It's the same with when we meet new people. We actually are pretty good as humans at deciding if somebody is trustworthy or not. Doesn't always work. Untrustworthy people get into everybody's lives, but there are various signals that people pass. It's the same with systems. If they meet the confidentiality, the integrity, and the availability criteria that we set, they can be said to be trustworthy, i.e., they're worthy of trust. Whether we trust them or not is up to us to test. So how do we test for trust, the relationship of trust? Well, we evaluate these variables, we evaluate these trustworthiness variables, and we do that through certification, accreditation, and assurance activities. So certification is where a standard is given. You must meet this standard. It can be technical or non-technical, and it determines compliance. Once you comply with that standard, it meets a specific set of security requirements. Then you can record the conformance or non-conformance of your system, and also, again, a certification may be just valid for a certain length of time or a certain part of the mission, so it might need to change over time. Accreditation, on the other hand, is where an approval authority, usually an external assessor or somebody like that, goes through and authorizes the management and operation of a system, what they call the targeted evaluation. They have a targeted evaluation and they test it and retest it. They use their expert knowledge to understand where these threats and weaknesses are. And it's a statement. He comes out with a statement, and that statement effectively says, well, this is a secure component because we've run these independent tests about confidentiality, integrity, and availability. And these are all measured, if you like, against these protection profiles we talked about earlier, where our expected assurance levels have been met. Assurance, on the other hand, is the trust related to the presence of security capabilities. So some people, one thing that these people say about trust is sometimes trust is granted and sometimes trust is earned. Security assurance is about how has your system earned the trust of the operators. So you can only evaluate this once you've actually getting operation. Once you're getting into operation, you start to measure, you accept the capabilities, you understand the security flaws, for want of a better word, or weaknesses, and you know the level of assurance that you have that system is working correctly, etc. Again, an example I gave earlier was like where you'd have one component like a power cutoff switch that you might just only implement in a pilot capacity first, but once it had run for a while, you might roll that out to the other items in your fleet. So therefore, assurance is a little bit like, we've seen this before, we've done this before, so therefore we need to worry a little bit less about the security of those components because we know that they work under pressure. So the trust has grown, if you like, the trust has been formed, and it's justified throughout the life cycle of the system. And also, it's only when you're doing this longitudinal process that you understand that safety, resiliency, and other emergent properties are actually present. And that includes security, an emergent property of the system. So you will carry that out assurance throughout the life cycle of the system, but assurance is not forever. There are, for instance, changes, legal, environmental concerns, let's say sustainability. I know there's a lot of legislation, etc., about space debris, about pollution levels, about materials used, etc. So these requirements will change from time to time, and the performance metrics will also change. So you need some kind of way of revisiting the assurance from time to time with these re-evaluated environmental concerns. When I say environmental, I mean background concerns. So even if the system never changes, it's still going to have an end of life scenario because the threat environment changes all the time. And therefore, you need to think of operational security, operational activities with which you can monitor and understand the health of your space mission. So thank you for sticking with me so far. Here's a quick summary and a few conclusions. So I've outlined a methodology of how we establish trust and trustworthiness in systems, how we can provide a way to analyze potential security weaknesses, potential security vulnerabilities that may spread between the systems and the components. They may be common, and how we would come to counteract those, how we would get around those or mitigate their effects. And this means that your business strategy, your business objectives are more likely to be followed through to successful implementation because you're employing risk management techniques, threat analysis, threat scenarios, and putting in controls. It also means that you need to think about it being transparent and traceable. Again, many large manufacturers of aircraft and space hardware have had their problems with configuration and traceability. But only in doing that, only in keeping those, tracing those changes, can you see and demonstrate that you've fulfilled your security objectives. And also ongoing assurance to accommodate the dynamic risks which happen in operational use. And like all good academic talks, there's a little bit further research. So I've talked on a methodology, the SSE for space methodology that was developed and used in the ESA environment. And one of the things that comes out of that is that you define a controlled vocabulary, a glossary, things like protection profiles, things like security profiles, controls, etc. And these form a taxonomy with which you can work, but only when you work with a whole ontology which combines both the objects and the relationships between them, can you seek to assure a system of systems. When it's a very complex system, lots of subsystems and components, you need that full overview, full traceability. There's many different engineering psychological factors in play. I would imagine that financial factors are a big factor when it comes to things like security measures. But we also need to think about what are the effects on trustworthiness and trust. To what extent can we prove that what we've put in is a help and not a hindrance? To what extent will it help us meet our business objectives? Again, this idea of new space, commercial pressures coming in all the time, timelines and the actual life cycle of missions is becoming compressed. They're just taking less time to reach operational stages, and the always kind of changing regulatory field that applies to this. So, on which point I would maybe like to finish, ask you for any questions if you enjoyed the flight, and thank you very much for your attention.
Duncan, that was exceptional. Thank you very much. And again, we really appreciate your time. I have a couple questions. First off, I really enjoyed hearing about the different profiles and how those relate to the business objectives and the security objectives, seeing that thread translated throughout the entire cybersecurity development process. That was really useful for me, and especially seeing it contextualized within the life cycle. So that was something that I had not seen before, and big fan of ontologies. So I appreciated that you added that in at the end. So the first question pertains to those security profiles. The profiles. The main question is: are these standardized? You spoke about some that ESA performs, but it sounded like ESA did it on a case-by-case basis. What is the status of security profile standardization, or at least tailoring security profiles for a given mission?
Okay. Well, as I kind of mentioned, that security profiles are much more tangible than protection profiles. So They are often bold statements of fact. We need to put these controls in, and in order to meet this requirement. The protection profiles generally are sourced from the ANISA assurance requirements, and the common criteria, although if you were to print it out, would be a very large document, actually goes into a lot of detail about what things you need to look for, what kind of things you need to test in order to build that assurance, those that to ensure that you have met what you are specifying you want to meet. Um, so yes, there is
Okay.
always debate. Um, I'm not sure whether it's easily translatable into that, but it's getting there. I touched on that idea of ontologies. I saw from one of your earlier lectures that you talk about like a software function that hangs off a software program. It's easy, I say easy. It's relatively easy to see how a threat actor could present a threat to a software function, and then that way they could be incorporated into a more comprehensive ontology that would accommodate cybersecurity. So that's a good research thread right there, I
I
think.
I wholly agree, and I'd love to see the results of ontology for cybersecurity and spacecraft be still my heart. Um, so a follow-up question is, and this has to do with your summary conclusions, where you talked about the future potential. New space is always changing, new regulations are coming out. As we move into this proliferated satellite constellation and network architecture in space, moving into the late 2020s, early 2030s, what are you as a spacecraft cybersecurity professional? What are you most worried about?
Wow. Wow. Okay, so one of my lecturing duties has included computer architectures and operating systems. And the threats have kind of morphed. I was reading recently about how satellite clusters will be operating on a data center model, so that there's the communication between the data center, which is also in orbit, by the way, and the satellites. Now this gives you side the threats then morph into management of that data center, if you like. So in the same way that we've moved to cloud in our terrestrial activities, we need to ensure separation of duties and certification for those who provide services to others. So I see that as being a big challenge going forward. Um, the kind of paper about um, there was a paper presented. I was one of the 82 co-authors on that paper um, about an international standard for cybersecurity, which I think is a long way off still. But it needs to take into account IP-based systems because they are kind of, if you like, one of the protections for space-based systems is the use of space data protocol, which is less common than an IP protocol. If you start to overtake everything with IP, it becomes just another extension of the internet and all the horrors that might bring with it. So, um, yes, there's lots of different ways this could go, but there are very few threats that are specific to space. They will have all manifested themselves, hopefully, on Earth first. So yeah, some other stuff we've been looking at is with AI and ML about cache poisoning the models that automated spacecraft might use. This is a vector that is emerging, if you like, as one of the problem areas. So yes, plenty to go at. I think plenty to go at.
Duncan, thank you very much for your expertise, for your time, for the insight. I know that this was personally quite helpful. Um, We appreciate you, and hope you come back with the advanced seminar for cybersecurity. So
Brilliant.
thank you.
Thank you very much. Thank you. Thank you. I will sign off now, I think.